everyone, this is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, we are going to discuss the introduction related to the analog electronics subject. So, while coming to the contents, we are going to discuss what is meant by analog signal and what is meant by electron and what is meant by electronics and what is meant by analog electronics. And in order to understand this subject, what are the prerequisites required for this subject, we are going to discuss, that is AC/DC sources and electrical components as well as semiconductor materials. So before going to the analog electronics introduction, first of all we have to know about analog signal. So the analog electronics is the combination of analog as well as electronics. So that's why we are going to discuss first what is meant by analog signal, and then what is meant by electronics, and then we'll move to the analog electronics. So in this, what is meant by analog signal? So this analog signal is a continuous signal that contains time varying quantities. So these analog signals in most of the cases we will represent with either a sinusoidal signal or a cosinusoidal signal here. So any signal, if it is varies with respect to time, that particular signal we are calling it as the analog signal here. So this particular analog signal we can represent here with like this. Taking the sinusoidal signal with, it is varying with respect to time, measured in seconds, and this is, I am taking here it as the voltage signal, or else we can also take it as current signal. That may be the voltage or current signal, and this value indicates the positive amplitude, or let's say I am indicating, and this value indicates the negative amplitude or minus A. So the V peak to peak voltage is this much. This is the peak to peak voltage of the analog signal. So this particular analog signal is varying with respect to time here. So any analog signal can be defined by using its amplitude and its frequency, or by its phase here. So what is meant by amplitude here? So this portion of the signal indicates the amplitude of the signal here. So this is the positive amplitude or positive peak of the signal, and this is the negative amplitude or negative peak of the signal here. And the phase angle here, it is 0 degrees. Okay, here it is 90 degrees, here it is 180 degrees, and here it is 270 degrees, and here it is 360 degrees. This is the phase angle of the signal here. And similarly, the frequency of the signal we can indicate by taking the inverse of the time period. If we indicate the time period of this particular signal 1 by t, that will give the frequency of this particular signal. Suppose if I am taking my t value as 1 milliseconds. So if I wanted to calculate the frequency of this particular signal, I will get it as 1 into 10 power minus 3 is 1 kilohertz. So this is the frequency of the particular signal, whatever we considered here. So the amplitude indicates the height of the signal in the positive direction as well as in the negative direction, and the phase angle indicates at what, at particular point how much amount of phase angle it is providing. Okay, and the frequency indicates how much amount of frequency this particular signal is varying here. Okay, these are the different characteristics or parameters of the analog signal here. So while coming to the characteristics of this analog signal, so these type of signals are time varying signal. Just now we have seen this particular signal is continuously varying with respect to the time, and the minimum as well as maximum values, which is either positive or negative. So the minimum value indicates the negative peak or negative amplitude of the signal, and the maximum value indicates the positive peak or positive height of the signal here. And these analog signals are available in the periodic form as well as in the non-periodic form. So here periodic signal is nothing but that particular signal repeats its cycle. One cycle of that particular signal is repeats for every cycle. The same signal will repeat for every cycle here. But in the case of non-periodic signal, the shape of the signal, or if any signal it is there in that particular duration one type, means in the next cycle it will be not similar to the previous cycle. So that kind of signals are the non-periodic signals here. So here the periodic signal x of t, and after next cycle, after some time period t plus t, these must be equal here. Both x of t and x of t plus t are equal in the case of periodic signals. So we can write it as x of t is equal to x of t plus t here. So after one cycle or after some t period also, it is showing the same signal in the case of periodic. And in the case of non-periodic signal, if we take the x of t, and if we take the x of t plus t after some time period, it will be not equal to the previously what is the signal we have taken the previous cycle. So these are the non-periodic signals. So the analog signal, for example, whatever we considered in the previous slide, can be available in the periodic form as well as in the non-periodic form. And always the analog signal will work on the continuous data. Why? Because it is varying with respect to the time period continuously. And the accuracy of the analog signal is not high here. Why? Because it is continuously varying with the time. There is a variation in the amplitude values as well as the frequency values as well as the phase angle values of the analog signal. So that's why we cannot say it is the 100% accurate signal, though it is the AC signal. And next, it will use it to measure the natural or physical values of the any particular thing or any particular device here. These are the different characteristics of the analog signal, and where we can use this particular analog signals. So in order to see the performance of any electronic component or any electronic device, the first thing we required here it is analog signal. By application of the analog signal, we can able to verify the performance of any particular device here. Okay, so any real world equipment or any real world electronic or electronic circuits, we can see the operation of that one by applying the analog signal as the input to that. And what is the basic disadvantage of an analog signal? See, this analog signal is not resistant towards the noise. That is nothing but it is always, it is very easy to cope up with the noise. So we can expect noise along with the original signal in the case of analog signals. So therefore, because of this noise present in the signal, we may get distortion in the output of the circuit. We may get the distortion in the output of the circuit, as well as it reduces the transmission quality of the signal. And we cannot fix the particular range of this analog signal here. So this is the drawback of the analog signal. So when we are going to utilize this particular signal to apply for any circuit, we have to check whether it is the noise percentage is less or not. Anyway, in the practical case, we may not remove the total noise which is present in the signal, but we need to maintain that noise value should be minimum to utilize for our applications. So that's why we need to check whether it is a low noise signal or high noise signal. And what are the examples of these analog signals? So the video signal, whatever we are getting from the television or picture or any video, any image, this belongs to the video signal here. And human voice in the air is also one of the analog signal. It is in the form of waves. And the radio transmission waves, the radio RF waves are also belongs to the analog signals. And TV transmission waves, these are also belongs to the analog signals. These are some of the examples of analog signals. Along with this, we are also having so many types of analog signals here. And next, what are the applications of these analog signals? So these basic application is in order to check the performance of any electronic circuits, and along with that, it is also utilized in the communication systems. Okay, in order to convey the voice, data, or image signal, or else video information using a continuous analog signal here. So these are the basic applications of the analog signal in all the communication systems, in the transmission as well as the reception, and as well as the video information and the signal information. We are going to utilize these analog signals. And we discussed about the analog signal, and next we are going to discuss about the electron and then by electronics here. So here electron is one of the negatively charged particle of an atom here. Okay, this is the negatively charged particle of an atom here. So in order to understand that, I have taken atomic structure here. So this atom consists of three charged particles. One is the proton. So proton we are indicating with the plus symbol. Why? Because proton is having the positive charge. And second one is the neutron. So neutron is not having any type of charge, that may be the positive or negative charge. It doesn't have any charge. And electron is having the negatively charged particle, and always it will available at the outer shell of the nucleus or outer shell of the atom here. So that's why all the electrons are moved or surrounding across the outer shell of the atom, and the protons or neutrons are across the nucleus here. And here if we take one particular electron, each electron will carries 1 unit of negative charge. So that value is 1.602 into 10 power minus 19 coulombs here. So the each electron will carries 1 unit of the negative charge, and that value is this much. And the electrons are very less massive than protons. So the weight of the electron is very less compared to the proton here, and that is 9.10938 into 10 power minus 31 kilograms. So this is the weight of one particular electron, and the symbol utilized for the electron is e power minus 1, or else by using the minus symbol also we can represent the electron, or also by using the dot also we can represent the electron. And similarly, to represent the proton we can utilize either plus symbol or circle here. So this is about electron. These particular electron we are going to utilize in the electronics here. So what is mean by electronics? So here electronics is the study of how to control the flow of electrons. Okay, we can define the electronics as the study of how to control the flow of electrons in a gas or a vacuum or in a semiconductor device. If we take any type of material or gas or anything, in that how the electron flow is there, that is indicated by the electronics here. So, and we can also define this electronics is the field of science and engineering which deals with the flow of electrons through a vacuum or a gas or semiconductor material. So that indicates the electronics here. See, olden days all the electronics or electronic devices are designed with the vacuum tubes, and later on designed with the gas, but nowadays any electronic device is designed with the semiconductor materials here. Why we moved from vacuum to gas and gas to semiconductor here means, if we design any electronic device with a vacuum, it will take very high space, and the size of the system will be high, and the cost of the signal system is also high, and the power consumption is also high. Okay, and the speed of the system will also less here. It is decreased here. So these are the drawbacks of utilizing the vacuum tubes to design the circuits, and later on moved with the gas. And if we design the circuits with the gas also, we are getting some problems. So that's why nowadays we are utilizing the semiconductor materials. So if we design an electronic device with the semiconductor material, the size of that one will be decreases, and the cost is also decreases, power consumption is also decreases, but the speed of the system will be increases here. So because of these reasons, we are replacing the vacuum tubes with the semiconductor materials, and the size of this one is very very less, so we can integrate so many number of semiconductor elements, so many components on this semiconductor material here. And the devices in which conduction is due to the flow of electrons are called electronic devices here. And what is meant by analog electronics here? So here analog electronics are electronic systems with a continuously variable signal. That is nothing but if we when we can say particular system is analog system, here it is. Okay, analog system or analog electronics, when we apply one particular signal to this, and what is the output we are getting here after some process, which type of system we are going to utilize, it depends upon that we can expect the output here. So this process of seeing the performance of electronic systems by using the analog signals is nothing but the analog electronic systems. And what are the major applications of this analog electronics? So these analog electronics mostly utilized in the radio and audio equipment, and wherever the signals are derived from analog sensors and transducers prior to conversion to digital signals for subsequent storage and processing. That is nothing but in any communication purpose, radio and audio communication purpose, as well as when we utilize for the digital systems, first of all, we will take the analog signal and analog system, and then we will convert into the digital form by utilizing the sampling and quantization process. Then only we can utilize for the digital processing in order to store and processing that particular digital information. So these are the major applications of the analog electronics. And what are the prerequisites required for this analog electronics subject? So the prerequisites required for this analog electronics are which type of sources we are going to utilize, that is AC or DC sources, and which type of elements we are going to utilize to design the analog electronic circuits. Those are resistors, inductors, and capacitors. And materials, which type of material we are going to utilize, that is semiconductor materials we are going to utilize to design the analog electronics. So in that we are going to see with the AC-DC sources now. So while coming to the AC-DC sources, we are having the AC voltage or DC voltage, alternating current form as well as direct current form voltages here. And along with that, we are also having AC current as well as DC current, alternating form current and DC current form. So always the AC signal we will indicate with the sinusoidal form or in the sinusoidal signal, and DC signals we are indicating with the straight line. So this we will indicate in the circle like this, but the DC signals we will indicate with a plus or minus in the circle here. Okay, AC as well as DC signals. So from the main power supply, we will get the 230 volts AC supply only. But in order to utilize for our home appliances or any practical appliances, we will convert this AC into DC by using the rectification as well as regulation as well as filtering process. So from that we will get it as the DC signal. Then that particular DC signal we are going to utilize for our home appliances or else any practical appliances. So generally, while coming to the AC and DC sources, so if we see the battery, we will indicate with this long line and short line. So this is the positive polarity. It indicates the positive polarity of the battery and indicates the negative polarity of the battery. Okay. And this positive polarity and negative polarity we will indicate with the plus symbol as well as minus symbol. So that battery we are indicating with battery with polarity labels. And ideal current source we will indicate with like this, and the ideal voltage source with the horizontal line. with the vertical line, ideal current source with the horizontal line, and this one indicates the AC signal or oscillator generated alternating current source. The AC signal, the one of the source to generate the AC signal here, it is the oscillator circuit. That is the amplifier with the positive feedback circuit. If we utilize that particular circuit, we can able to generate any kind of analog signal here. And well, coming to the AC current source. So AC current source we will indicate with a circle within the sinusoidal signal and in the downward direction. And AC voltage source with this indication, and the DC current source within the circle with plus or minus, as well as DC voltage source within the circle plus or minus symbols. So these are the important things or important source symbols required to design the devices and in order to utilize in the devices to see the performance of the electronic devices. And next prerequisite is about RLC elements of resistor, inductor as well as the capacitor elements. So if we understand the function of these particular elements, we can able to design the different electronic circuits and along with some other active elements also. And resistance. Well, coming to the resistance, we will represent the resistor with the capital R here, and it is a passive element and it consists of two terminals. Okay, these are the two terminals of the resistor, and we will represent the resistor with this particular symbol here. Okay, and the that implements the electrical resistance as a circuit element. So in electronic circuits, resistors are used to reduce the current flow or adjust the signal level, or in order to divide the voltages, and in order to bias the active elements, and in order to terminate the transmission lines among the other users. So the basic function of the resistor is to oppose the flow of current within the circuit, or in order to control the flow of current in the circuit. And this particular resistance will measured in ohms here. And the particular resistance value we can calculate by using the different bands which are present on the resistor. So in the labs we are having these type of resistors with the different codes. So by using this particular formula, that is BP, Roy, has very Great Britain has very good wife here. So by using these things, by using these colors, it is having the different values. This is black, this is brown, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. It is W, sorry. So with these, it depends upon these, we will see the values of this. Here red means here it is having 2 here, and violet means 7, and black means 0 here, and this orange indicates the, it is 10 power 1, 10 power 2, 10 power 3, 10 power 4 into 10 power 4. So the total value of this one is 270 into 10 power 4. Okay, so this one is 2700 kilo ohms is the value of this particular resistance. So by using this band values of the resistance, we can able to find the value of any resistance here. So if you want to take 1 kilo ohm resistance, means we have to see from this color code table, we have to estimate the value first. 1 kilo ohm means first should be brown, okay, and second should be black, black, black. That is, this is black, black, black here. So the value of this one is 1 kilo. So we need to take brown, black, black, black to get the 1 kilo resistance. So in this way we need to calculate the resistance value of any particular resistor that will be utilized to do the experiments in the laboratory. And next one is the capacitance. So this capacitor is a device which can be used to store the electrical energy in the form of electric field here. So it is also a passive component with two terminals, and the effect of the capacitor we can call it as the capacitance. So for generally the capacitor we will represent with the two parallel plates. It is one parallel plate and this is the one more parallel plate. Generally we will represent one with the positive charge and second one with the negative charge. And the in between these two, this medium is the dielectric medium, and it acts like an insulator, and these two parallel plates of the capacitor acts like a conductors, and the dielectric medium between the two plates acts like an insulator here. So this is one of the capacitor I am showing here with the value of capacitance is 100 microfarads. So here the capacitance is measured in farads here. Capacitance we are measuring with the farads here. Here we are having different type of capacitors. Those are electrolyte capacitors or ceramic capacitors, etc. So depending upon our requirement in the practical applications, we can choose any one of the capacitor here. And next one is the inductance. Here inductance is also a passive element or component with two terminals, and we can also call it as the coil or choke or reactor. Okay, and which will stores the energy in the form of magnetic field when electric current flows through it here. Okay, and this inductor consists of an insulated wire wound into a coil around a core here. So that's why it is indicating like this. It is the core of the inductance, and it is measured in henries here. In the inductance also we are having inductors also we are having in different sizes and weights and different types, and depending upon our practical applications we can utilize any one of the inductor here. And the third prerequisite is required for the analog electronics is the semiconductor material. So before going to the semiconductor material, first of all we have to know what is meant by material. So here material is nothing but it is one type of substance which is used to make up of physical object. That is nothing but in order to design or in order to make something we are using some material, means that belongs to the material. We are using some substance to design something or some object. That particular substance we are calling it as the material here. So here we are having two types of materials here. Those are the crystalline materials and non-crystalline materials. So while coming to the crystalline materials, these crystalline materials are having some shape. We are having some shape, and solid materials such as atoms, molecules or ions comes under the crystalline type of materials here. So second type of materials are the non-crystalline type of materials. These are having materials without shape here. Okay, it doesn't have any particular shape, and most of the cases we are not going to utilize these type of materials to design some objects here. Most of the cases will prefer the crystalline materials only. So that's why I'm going to discuss about the crystalline materials. And again, in the case of crystalline materials, we are having three types. Those are insulator, conductor, as well as semiconductor materials. So now we will discuss about these three types of crystalline materials. So if you take one particular crystalline material, how we can able to differentiate or how we can able to know whether it belongs to the insulator or conductor or semiconductor material, that we can able to identify by using the energy band structure of that particular material. So what are the energy band diagrams of these three materials? We'll see now. So these are the energy band structures of materials here. So this is for insulator, for semiconductor and conductor. If we take the energy band structure of any particular material, it consists of the conduction band and valence band, and the gap between this conduction band and valence band we are calling it the forbidden gap. Okay, forbidden gap or also called as band gap. Okay. So this is the energy band structure of particular material. So here always the conduction band will filled with a more number of electrons and the valence band with a more number of vacant electrons or free electrons. If we apply any electric field or voltage to this particular material, because of that force or because of that voltage, the valence electrons which are present in this valence band will try to jump to the conduction band here. So the conduction band will collect the electrons from this valence band here. So these are ready for conduction here. These electrons are ready for conduction now here. So this is about the energy band structure of particular material. I have taken here it as example. But now in the case of materials, different types of materials, this energy band structure will be different here. So, well, coming to the insulator circuit. So, insulator is one of the crystalline type of material. It is offer very low level of conductivity when we apply the voltage to it. So, why it is offering very low conductivity level? This insulator, why it is providing very less conductivity here it is means, if we see the gap between this valence band as well as conduction band in the case of a insulator, it is very high, almost 9 electron volts. So there is very much gap between the valence band and conduction band. So because of this large band gap, when we apply the voltage to this also, the valence electrons or the free electrons which are present in this valence band are not reaching to this conduction band. So there is no electrons in the conduction band. So because of that reason, it is not providing any current here and it is not ready for conduction here. Because of that reason, the insulator is having zero conductivity. In the ideal case, we can say it as it is having zero conductivity. And the examples for this insulator material are paper, mica, glass or quartz. So these cannot able to pass the electric voltage through them. And the resistance level of this insulator is very high. Why? Because the current value is very less or zero here. So the resistivity of this insulator is 10 power 10 to 10 power 12 ohm centimeters. It is very high. And second type of crystalline material is the conductor. So the name itself indicating the conductor is a material which supports the very high flow of charge when a voltage applied across its terminals. So that we can say it is having very high conductivity here. Why it is providing very high conductivity? This conductor material means, if we observe the energy band structure of this conductor material, both the conduction band as well as valence band are overlapped here. Okay, both the conduction and valence band are overlapped here. So here this is the valence band and this is the conduction. Both are overlapped here, and the band gap, okay, the band gap between both the bands are zero here. So because of that reason, whatever the valence electrons which are present in the valence band are combined with the conduction band, and all the electrons are ready for conduction here. So that's why the value of conductivity is very high and the current is very high in the case of conductors. And the examples for this conductor materials are copper, aluminium, gold and silver here. So in the case of conductor, the resistivity value is very less. Why? Because the current value is very high. That is 10 power minus 4 to 10 power minus 6 ohm centimeters is the resistance value of the conductor here. And next type of crystalline material is the semiconductor material. Here a semiconductor material is having conductivity lies between the insulator as well as the conductor. That is nothing but the conductivity is less than the conductor but more than the insulator in the case of semiconductor material. It is not very high right? It is not very low. It will maintain medium range of conductivity. So that's why it is named as semiconductor. The conductivity level is less compared to the conductor material here. So the resistivity level is also in the medium range, that is 10 to 10 power 4 ohm centimeters in the case of semiconductor material. So the best examples for semiconductor materials are silicon and germanium. So nowadays any electronic component or device is designed with either silicon or germanium semiconductor materials only. Okay, so in this case, if we see the energy band structure of the semiconductor material, the energy gap or bond gap between the valence band and the conduction band is very less, that is only 2 electron volts only. So it is having very less gap. So when we apply the voltage to this, the valence electrons which are present in the valence band will jump to the conduction band, and now they are ready for conduction here, and there is a flow of current in the device. Okay. And the energy level of different materials, semiconductor materials, I have mentioned here. The energy level for the germanium material is 0.6 electron volts, and the silicon is 1.1 electron volts, where 1 electron volts is nothing but 1.6 into 10 power minus 90 joules. So these are the important things need to remember for solving the problems. And so here I have already mentioned among the 3 types of materials we are going to utilize the semiconductor materials to design the circuits. So we are having 2 types of semiconductor materials, that is silicon and germanium here. So that's why I have taken the atomic structure of the silicon and germanium materials. So if we see the silicon as well as germanium atomic structure, the outer shell of or outer orbit of the silicon material as well as germanium material are having 4 valence electrons. That is nothing but 4 free electrons, we can say. These free electrons are ready for conduction here. The electrons which are present in the inner orbits are not utilized for the conduction. Only these will utilize for the conduction here. And these semiconductor materials are of 2 types here. Those are the intrinsic semiconductors as well as extrinsic semiconductors. So these intrinsic semiconductors are nothing but the pure form of semiconductor materials. Those are germanium and silicon materials. In this case, the electrons as well as holes are same in this particular germanium and silicon materials. In the pure form of intrinsic semiconductors, the quantity of electrons as well as holes are equal here. And in the case of extrinsic semiconductors, from the intrinsic semiconductors only we can able to get the extrinsic semiconductors by using the process called doping here. So doping is nothing but adding some impurities to the intrinsic semiconductor to make it as the extrinsic semiconductors. Okay, so these extrinsic semiconductors are of 2 types, that is N-type of semiconductor materials and P-type of semiconductor materials. So to get this N-type of semiconductor materials, we need to add pentavalent impurities to the intrinsic semiconductors. And to get this P-type of extrinsic semiconductor material, we need to add trivalent impurities to this intrinsic semiconductor. So what are the pentavalent impurities here? Phosphorus, arsenic, antimony are the pentavalent impurities, and gallium, boron, indium, aluminium are the trivalent impurities here. So in the case of pentavalent impurities, the electrons are the majority carriers, more number of electrons will be present. And in the case of trivalent impurities, more number of holes will be present. So if we add these pentavalent impurities to the intrinsic semiconductor, more number of electrons will be present in the material compared to the holes here. So that's why the electrons are high compared to the holes here. So because of that reason, we are calling it as the N-type of semiconductor materials. Why? Because negative charge is higher than the positive charge. Electrons are more than the holes. And similarly, in the case of p-type of semiconductor materials, the holes are having more compared to the electrons. So that's why holes are having the positive charge. So that's why these are called as p-type of semiconductor materials. So now we will see how we can form this n-type as well as p-type of extrinsic semiconductors from the intrinsic semiconductors. So I have already mentioned intrinsic semiconductor is a pure form of semiconductor. In this case, the equal number of electrons and holes which are present in the circuits. So here I have taken the intrinsic silicon material here. If we observe here, all the silicon crystals are having the equal number of electrons. No extra electrons or holes which are present in this lattice. So these are forming the covalent bond with the nearby silicon atoms here. And here this one is forming covalent bond with this one and this is forming with this one, but these two are the valence electrons. If we add one more silicon atom here, this will form the covalent band with that particular silicon atom here. So these are having some valence electrons or free electrons. And how the conduction will be done in the case of intrinsic semiconductor here. So in the case of intrinsic semiconductor, I'm taking the atomic structure of that intrinsic semiconductor or cross section of atomic structure. Here I have taken the germanium material. Okay, so each germanium material is having 4 free electrons or 4 valence electrons here, and this is the nucleus of that germanium atom. And in this case, if we apply any energy or heat to this particular germanium material, the electron which is present here will try to move here. Okay, and once the electron is moving here and forming the covalent bond here and it leaving one space, it creates one hole that we are indicating with the circle, that is the hole here. And next, the electron which is present in the next atom will try to jump here. So like this, in this way, all the electrons will jump to the next of that atom and form a covalent bond here, and there will leave the hole there. And while coming to the extrinsic semiconductor, so even though we are having the intrinsic semiconductor, why we are moving for the extrinsic semiconductor here? In the case of intrinsic semiconductor, the number of charge carriers are equal here, so that the current conduction level is medium range or less here. So in order to utilize it for designing the circuits or devices, the conductivity level of intrinsic semiconductor must be increased here. So how we can able to improve that? By adding the impurities to the intrinsic semiconductor. So if we add the impurities, it will become the impure or extrinsic semiconductor. And I have already mentioned the process of adding impurities to the semiconductor is nothing but the doping here. So N-type of semiconductor here. So how we can make the N-type of semiconductor material? So in order to understand that, I have taken silicon crystal doped with the pentavalent impurities. So I have taken phosphorus as the pentavalent impurity and silicon as the intrinsic material. This is the impurity we are going to add. It is the pentavalent impurity. Pentavalent impurity means it is having 5 valence electrons in the outer shell of this atom. So here if you observe, this is the phosphorus atom here. It is having 5 electrons here. 1, 2, 3, 4 and 1 is vacant here. So the 4 valence electrons of this phosphorus forming the covalent bond with the 4 valence electrons of nearby silicon atoms, and 1 is free here. So each and every phosphorus and silicon atoms covalent bond will leave 1 free electrons. So because of this forming the covalence band between these atoms, more number of electrons will be increases in the material. So that's why it is called as the N-type of semiconductor material. Why? Because electron is having negative charge. And next, P-type of semiconductor material. If in this case I am taking again silicon material as the intrinsic material and I am taking boron as the trivalent impurity. So trivalent impurity means it is having 3 valence electrons only in the outer shell. So if you observe in this crystal lattice structure of silicon doped with boron, so this boron, so each valence electron of this boron form a covalent band with the nearby silicon atoms, but one is whole here. So there is no electron is there to form a covalent band with the other atom of this electron. So it is making the one hole here. So because of adding this more number of trivalent impurities, more number of holes will create in the case of P-type of semiconductor material, and holes are having the positive charge. So that's why these are called as the P-type of semiconductor materials. So in this session, we have discussed what is meant by analog signal and how we can utilize that analog signal, and what is meant by electronics, and what is meant by analog electronics, and what are the prerequisites required in order to understand this analog electronics subject. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.